Hello class. In this lesson we're going to learn how dilations map different types of figures. So first off, what do you think you get if you dilate a segment? You still get a segment? Yeah, you should. It should be the length should be r times the length of the original. So for example, here we have a segment, PQ. We want to dilate that using a scale factor of 2. And look at that, we get segment P prime Q prime, and that is indeed a segment. And how has it been changed? How has it been transformed? Well, its length is different. Right? You multiply the length by the scale factor. So if we're looking on the coordinate plane, we know that if we dilate using the origin as our center of dilation, you just multiply the coordinates by the scale factor. For example, just multiply the x and y coordinates here by 4 to find out where A prime is. And you can do that for any points that are on the segment. Now, what if you're not on the coordinate plane? How can you figure out what happens to segments when you dilate them? Well, there's a few different cases. The first case is what happens when the scale factor is 1. What happens when you do a dilation? Well, you know, that's the identity transformation. So the segment doesn't change. It stays invariant. So yes, you still get a segment. Another case that could happen is what if your center of dilation is on the line that passes through those 2 points that you're dilating? Well, you know that the dilation is going to map Q to Q prime. That's going to be somewhere on ray OQ. And similarly for P, P is going to be mapped to P prime somewhere on OP. And since those rays are all parts of that line, everything's collinear. So you will indeed, again, get a segment. And what happens when your center of dilation is not on that line that passes through the 2 points? So for example, what about when we get a picture like this? Well, we know how we can find out where P prime and Q prime are by doing a dilation. And we know that we have a side splitter here. And so we know that lines PQ and P prime Q prime are parallel. So we get the endpoints map like we want them to. And any point in between them, say point R, if we follow the rules for the dilation, that will also lie on our segment that we want. So any point in between gets mapped in between P prime, Q prime. So we do get another segment. So therefore, we have these 3 facts that we just showed. So a segment will map onto another segment. What happens when we try to dilate a ray? When we dilate this ray using scale factor of 2, we get another ray. And how has it been transformed? Well, the segment part, I'm sorry. So PQ, like we saw before, you'll multiply that length by the scale factor. So how do we know this holds true for all rays? Well, a few different cases again. The first case is when the scale factor is 1. Well, if it's 1, once again, it's staying invariant, so it's still a ray. Case 2, let's see, we want to see the line that contains ray PQ does not contain point O, the center. What do we get when we dilate and the scale factor is not 1? Well, we have a diagram that looks like this. And we know that PQ is going to map to P prime Q prime. We showed that before because that's a segment. But what about all the points that aren't on that segment? So let's call point there R. And we want to dilate R using the same scale factor. Is R prime going to be on that ray like we want it to? Yeah, R prime is going to be on there because we know that PQ and P prime Q prime are going to be parallel. Right? We learned that with dilations in side splitter. And similarly, if we look at PR and we do that dilation, that's going to be parallel. So those have to be the same ray. Our third case has a few subcases. What if the points, the center of dilation is on the ray? So if it's the same as one of the points, well, we should get the same ray. If we know that that's going to stay invariant. and Q is just going to move somewhere else on that side of the ray. So if we take any point that's not the center, it's going to either get pushed away from the center if it's an enlargement, or pulled towards the center if it's a reduction. So here's an example that shows that. And everything's collinear. And so we still get a ray. And so in this case, the ray stays invariant. So the points on it, let me say that again. The center stays invariant, the points get moved, but the rays are still equal. Sorry, you shouldn't really say they're invariant because the points on it are moving. So you can only use that term for something like the center of dilation that's not moving. Okay, what if we have endpoints P between the center of dilation and Q? Well, we just want to show that any of the points that are not in between O and P and not equal to them get pushed further away from the center than P does. So does X get mapped to X prime so that X prime is further away from the center than P prime is? Well, let's see if that holds true. Well, you know, OP is smaller than OX by how we found or defined X. And how are those lengths going to change when we do the dilation? Well, you know, we're going to multiply them both by R. And so how can we talk about the lengths of OP prime and OX prime? Well, if you multiply this inequality by R, and R is greater than 0, so the sign doesn't change, we see that OP prime is less than OX prime, just like we want. So the ray is going to be mapped onto a ray, just like we wanted it to. All right, and the rays, once again, are going to be equal. And here, our last case is when P and the center is in between P and Q, or the center is equal to Q, or when Q is between P and the center, what happens? Well, you can read through the details, but it turns out that you get a ray just like you would expect. So what happens when we dilate circles? Well, if the center of dilation is the same as the center of the circle, we end up having all the points moved away proportionally. So we end up with something called concentric circles. So we still get a circle. They have the same center. And what happens when your center of dilation is not the center of one of the circles, or of your original circle, I should say? Well, you still get a circle. It's just going to be either larger or smaller, depending on if it's an enlargement or a reduction. So, you know, rays map onto rays. The endpoints will map onto each other. If you dilate lines, that's a case of the rays. The lines will map will be dilated onto lines, and circles will be dilated to circles. So here's a little blurb that explains the part about lines dilating to give you lines. It's just taking the cases for rays and saying that you put two rays together, you get a line, so it still holds for lines. What about triangles? What do you think happens when you dilate a triangle? Making conjecture says make a hypothesis. That's all it means. Well, hopefully you still get a triangle. All the angles should be the same, and the side lengths will be proportional to the side lengths in the original triangle. So if we want to do an experiment, we can do a dilation with a triangle. So here is my dilation. And if we check all of the side lengths, they're all proportional to the lengths in the original triangle. And all the angles will be mapped to angles of equal measure. What do you get when you dilate a rectangle? What do you think happens? Hopefully you get another rectangle. And the ratios of lengths and the widths will be the same. So let's verify that with an experiment. Here's my dilation. And if we check all the lengths, let's see. And we can, this time we're checking the lengths within the figure. So if we're looking, we have 3 to 2, and the ratio over here is 1.5 to 1, and those are equal. So you can check the ratios either way. They should still be equal. And what do we get when we map regular polygons? We should get another regular polygon, and all the lengths should be proportional to the lengths in the original. And so if we do a little experiment, here we have a pentagon. There's our center down there, center dilation. And all those lengths are proportional like we wanted to, and all the angles are equal in measure. All the corresponding angles are equal in measure. Now, we want to look at what happens with angles. How do we show that the angles are dilated and we get angles with the same measure? Well, first, what happens when we have parallel lines cut by transversal? We know that the corresponding angles are equal in measure, the alternate interior angles are equal in measure, and the alternate exterior angles are equal in measure. So if we look at what happens when we dilate an angle, here's a picture of one way that can occur. So how can we prove that the measure of angle BAC equals the measure of angle B prime A prime C prime? Well, we know that since we have a dilation, these are going to be parallel. And similarly, these are going to be parallel. So 2 chevrons on there. Okay, so since we have parallel lines, the rays are parallel. So the corresponding angles here, BAC and B prime DE, those angles are congruent. The same goes for B prime DE and angle B prime A prime C prime. And so by substitution, we know that those angles are equal in measure like we wanted to show. So we know that angles are mapped to angles of equal measure, and the polygons map like we'd expect them to. So in this lesson, we saw how dilations map different types of figures. Thanks for watching this video.